Episode 12. How did computers talk to each other? Hi, I'm Foggy Michael, and welcome to Computers Before the Internet. Here's the question that started this whole episode. Computer A has a bit, a 1 or a 0, sitting over here. Computer B is somewhere else. How does that bit get from computer A to computer B? Because a 1 or a 0 doesn't literally travel down the line. First, the bit has to become something physical. The computer's electronics have to represent that bit using a physical signal. In a simple electrical example, we can represent a 1 with one voltage level and a 0 with another. So conceptually, we have this. Computer A creates the signal, computer B detects the signal and reconstructs the bit. Sounds easy. Except now we've got another problem. How does computer B know when to look at the signal? Timing. The two computers have to agree on the rules of the conversation, including the transmission speed. One method is called asynchronous transmission. When nothing is being transmitted, the line can sit idle. When A wants to send a character, a start bit essentially tells B that, wake up, here comes a character. B knows the transmission speed, so it knows when to sample the following bits. Then a stop bit marks the end of the character. So we have this. This made a lot more sense to me when I thought about somebody sitting at a terminal typing one character. Then I sit there thinking, maybe I scratch my head. Maybe I have a sip of coffee. God knows when I'm going to hit the next key. Of course, if this was a metered long-distance telephone call, the phone company didn't give a damn that I was thinking. For larger continuous amounts of data, there is synchronous communication. Instead of continually starting and stopping individual characters, the sender and receiver establish synchronization and stay in step while transmitting a stream or a block of characters. Data. I think of it like a train. Asynchronous, one car announces itself at a time. Synchronous, here's the train, stay in step with it. But what if a bit gets screwed up? Suppose A sends this, but because of noise or some other disturbance, B receives this. One bit changed. How does B know? One old simple method is called a parity bit. The computers agree on odd or even parity, and an extra bit lets the receiver check whether the received character still follows the rule. If it doesn't, something went wrong. Parity is useful, but limited. For larger blocks of information, there's a much stronger method called a CRC, or cyclic redundancy check. The mathematics can get pretty hairy, so we're not going to do that here. The easiest way I found to understand CRC is it's a mathematical fingerprint. A performs a calculation on the block of data and gets a relatively small CRC value. It sends the data plus a CRC fingerprint. B performs the same calculation on what it received. Fingerprints match, Probably good. Fingerprints don't match. Something changed. Don't trust it. There's some fascinating binary mathematics underneath CRC, including XOR, but we don't need to calculate one ourselves to understand what it accomplishes. And CRC doesn't necessarily fix the bad information. It tells B, hey, something got screwed up. So what happens now? ACK and NACK. ACK means acknowledgement. Got it. Looks good. NACK means negative acknowledgement. Nope, something went wrong. In a system that uses retransmission, a NACK can result in A sending the information again. So conceptually, or now we are beginning to have an actual, reliable conversation. Now, put a telephone in the middle. Old telephone networks were designed primarily for voice frequency signals. So how do we get computer information through that? Enter one of my old favorite computer words, the modem. Modulator, demodulator, modem. Modulation means deliberately changing some property of a signal so those changes carry information. In an extremely simplified example, imagine low frequency equals 0, high frequency equals 1. Then 1, 0, 1, 1, 0 could be represented as high, low, high, high, low. The modem at the other end recognizes those changes and reconstructs the bits. Real modems became considerably more sophisticated, but that is the basic idea. All those wonderful old modems and fax noises, those weren't meaningless noises. We were listening to signals carrying data. And here's the part that finally made everything click for me. I kept getting timing, modulation, parity, CRC, and ACK-NACK mixed together. Then I realized they're doing different jobs in the same conversation. Modulation. How do I physically represent it and send it? Timing. When do I read it? Error detection. Can I trust what I received? ACK and NACK. What do I tell the sender? Once I saw them in different departments doing different jobs, the whole thing finally made sense. Wait a minute, that sounds like radio. While learning about modulation, I suddenly thought, isn't this basically what AM and FM radio are doing? Yep. AM means amplitude modulation. FM means frequency modulation. Different technology and purpose, but the fundamental idea is related. Information can be carried by controlled changes to a signal. And that leads us from wired communication to wireless. With copper wire, information can be represented by electrical signals. With fiber optics, we are using light. With wireless communication, information is represented using electromagnetic signals transmitted through space. But here's the important thing. There aren't little ones and zeros flying around in your living room. The bits are represented by changes in physical signals. Different medium, same fundamental problem. How do I represent information physically, get it somewhere else, and reconstruct it correctly? And one more thing. Just sending billions of bits isn't enough. The computers need agreed upon rules, protocols so they can make sense of what they're receiving. Where does something begin? Where does it end? Where is it going? Did it arrive correctly? What happens next? Otherwise, computer A could dump an enormous stream onto the network and tell computer B, here are 10 billion random bits. Good luck. And now, think about the room you're sitting in. There may be signals carrying AM radio, FM radio, Wi-Fi, Bluetooth, cellular, television, GPS. Yet, I can turn on an FM radio, tune it to WICN 90.5 FM, and the radio essentially says, forget all that other stuff, give me this one, which leaves me with one hell of a question. How can all those signals be in the same air without becoming one gigantic electronic mess? And that is another story. I'm Foggy Michael. Thank you for watching.